Okay, so 10.9, last thing that we're going to deal with this chapter is independent and dependent events. And it's going to look similar to the probability we did earlier with the word and the word or. And so what you have to be careful about is to keep straight that these are different. And I'll try to explain that in a second. So we're going to have two terms. We're going to have independent event and dependent event. We'll take independent first. Independent events are two events where they occur at once, but the one has no effect on the other. So they're two events, but the one has no effect on the probability of the other. They're two events, but they're not really related. That's what we mean by independent. So you get two events, but the one does not have an effect on the other. In this situation, the probability, because you're looking at two things. So you're looking at a overall total probability. And it would be the probability of the first times the probability of the second. So that's pretty easy. You're going to be multiplying. So if you remember, probability can be represented as a fraction. And that's what we'll be doing here. We'll be multiplying the fractions. It could be represented as a percent. It could be represented as a decimal. In any of those cases, to find the probability of the independent event, and notice the subscript there of I, this is what tells you it's an independent event. And I just abbreviate it there. But it's that little subscript I, at least in the formula. What will really happen instead in real life is this. You'll be told about two events, and you have to think and consider whether they are independent events or not. Because the second thing we're going to do today is talk about dependent events. So again, if it's a word problem, you're not going to have probability of A and B subscript I to tell you, all right, do the independent event formula. You need to know that yourself. All right, so let me show you a few of them, so hopefully it'll make sense to you. Here's the first one, pretty simplistic. I have a game cube, just one, and I have a coin, and I'm showing you both sides of the coin. So we got a game cube and we have a coin. And so the first question would be something like this. If you rolled a game cube and flipped a coin, what's the probability of rolling a 4 and getting a tails? Now those are independent events. Rolling the first dice has nothing to do with flipping the coin. They don't interact with each other. They're independent of each other. And therefore this is an independent event. So somebody raise your hand and tell me what would be the probability of rolling the game cube. What's the probability of getting a 4 on the game cube? Brendan? 1/6. There's 1 4 on the game cube, and there are 6 total spots on the game cube, right? So there's 1 4 and there's 6 total spots. And then flipping the coin. Somebody raise your hand. What's the probability of flipping a coin of getting tails? Amber? 1/2. So this is a straight multiplication. Now, if it's possible, we would always, before multiplying, look to reduce, right? Arbum? You always want to look before you multiply. If you can reduce, there is no reducing on this one. Somebody raise your hand and tell me, how do you multiply fractions? What do you do to multiply fractions? Edward? And do, right. So multiply fractions, top times top, bottom times bottom. So we all know 1 times 1 is 1, and we all know 6 times 2 is 12. So the probability of being able to roll a 4 and also flip a tails is 1 out of every 12 attempts. Now, I know my GameCube rolls here. I don't know if my coin is going to flip. All right. My coin is supposed to flip. It's not flipping. Who's got a coin on him? Anybody got a coin? Anybody got a coin? Omar, you got one? All right. Can you flip a coin? Are you a good flipper? coin? You got one? You got one? Are you a good flipper? Who's a good flipper? Give it to Colby. I think Colby can flip a coin. Chuck it up to him. I promise you'll get it back. All right, somebody help out Colby.
Where'd it go?
It's over by Raph somewhere.
No, under.
Got it? There we go. Luke's smart. So let's pass it. All right, Colby, give me a flip. Even though this doesn't matter, right? The first attempt's going to be bad. Catch it and, like, turn it over. Is that how you do it? That's all right. We'll do it on the floor. And that is a head. Sorry, you're going to have to get up. So you can get up when you need to, or you can stand up and flip it. Okay, so we're 0 for 1. Here we go. Second attempt. All right, we got a 6, so it doesn't really matter, but go ahead, Colby. And what do we got?
Heads.
All right, so we're heads, so we're neither of those. And again, we got to get both. We're trying to go for a 4 and a tails. We're 0 for 2. There's a 5. Go ahead, Colby. Doesn't really matter, though. We're going to be 0 for 3, right? It's okay. There it is, 0 for 3. 0 for 4. 0 for 5. Uh-oh. Go, Colby. All right, it's going to be whatever it is. What is it? What does it say? No, it's whatever. When it falls, it's whatever it is. So we're 0 for 6, even though we got the 4. Oh, got another 4. Here we go. We got a shot. What does it say? Tails. There it is. We're at 1 for 7. All right. So, and again, we could keep going. We could keep playing with this, but you see how the two relate? So that first time we got a 4, we still had to get the tails on the coin, and we didn't. And so again, the probability of this taking place is 1 out of every 12 rolls. Does that mean that after the 11th time we were guaranteed on the 12th time we were going to get a 4 and a tails? No. Remember, there's no guarantee. It's just a probability out of every 12 attempts, one of them will be a 4 and a tails. So that's the idea. So go ahead and just figure out mathematically what the second thing would be there. Oh, there's my coin down there. All right, I'll do it on the second one. Go ahead and figure out the even and the heads. Thank you, Colby. And pass that coin back. So again, everybody figuring out what's the probability of these independent events of rolling an even number and also flipping a heads. Even and heads. All right, if you got an answer, give me a raised hand here. Emily, what do you got? 1 what? How many agree with Emily? 1/10. Ooh, let's see what else somebody else has. Chloe, what do you got? How many agree with Chloe? 1/4. Uh-oh, a lot of hands up. So hopefully you said there are 3 even numbers out of 6 on the dice, right? A 2, a 4, and a 6. And then again, the heads is 1 out of 2. And you're always going to R-bum, reduce before you multiply, and you end up with 1/4. So every 1 out of 4 times should be an even and a heads. So let's see how the probability goes here. All right, attempt 1, I don't even need to flip the coin. All right, there's attempt 2 is possible. Ha! We are 1 for 2. I'm going to keep going. Yep, 1 for 3, 1 for 4. All right, so that was it. We hit right on the probability. It just so happens that that is the case. All right, let's suppose we're at 0 again. I'm going to try one more time. All right, 0 for 1. All right, here's a possibility. 1 for 2. See if I can beat the probability. Got a shot. No, still 1 for 3. It's got a shot. I'm still 1 for 4. Again, it's just probability, right? It's just probability of whether something can possibly take place. All right, so we've got one other situation here with 2 spinners. But you can see that the spinners are different, right? So here we've got 2 spinners we're going to use. Each spinner is a little different. Go ahead and figure out the probability of a B and a 2. And then figure out the probability of a C and an odd. Go ahead and do both of those. Nia, what do you have for the probability of the B and the 2? And that would be correct. And Julia, what do you have for the C and the odd?
5 over 32.
Correct, 5/32. So you should have gotten 1/16 and 5/32. So 1 out of 16, 5 out of 32. All right, let's go for bottom one. Take too long. Let's do the top one. Let's see if what I'll get with a B and a 2. Wow, that thing's slow. Oh, impossible. Will I get a 2? Ah, 1 for 1. Oh, 1 for 2. 2 for 3. I'm already beating the odds big time, right? I'm already 2 for 3. 2 for 4. 2 for 5. 2 for 6. 2 for 7. And I'm going to probably stop at 10. 2 for 8. See again how you can get one of them and not get the other? 2 of 9. And 2 of 10, and I could keep going. Again, probability, it's probable that 1 out of every 16 times I'll get the B and the 2. So independent events, remember the one does not affect the other. Independent events, you multiply. Second situation is dependent events. Dependent events. What are dependent events? These are two events where the occurrence of the first changes the probability of the second. The occurrence of the first event changes the probability of the second. Drawing names out of a hat is this way if you go past drawing one name out. So to draw one name out is no big deal, but to have two events and to draw out two different names, now you do have a situation. For example, we took all of your names and stuck them in a hat. And what are there? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. There's 21 of you. So what would be the probability of on my first pull out of pulling Hayden's name out? 1 in 21. Right? What would then be, we'll make it more complicated, what would be the probability of pulling out Hayden's name and also Julia's name on the second attempt? And it doesn't matter who's when. Pull out Hayden's name, pull out Julia's name. Two different attempts. Well, the fact that we pulled one name out when we tried the first time is going to affect how many possibilities there are the second time. That's what we're talking about with a dependent event. So I'll try to show you a couple examples. So the formula is similar. It is the probability of A times the probability, but we write the second one a little differently. The probability of the probability of B slash A. And all this simply means is B in respect to A. In other words, the probability of B is a little different because of what happened in A. A changes B. All right, so let's see if I can illustrate this with the hat. 10 names are placed in a hat, and 2 names are drawn out. So what's the probability of drawing out Ted and Sue? And the order doesn't matter. What's the probability that we'll get both Ted and Sue out of 10 names in a hat? So the first time, we're going to do the probability of Ted, right? So this first one is the probability of Ted. And Edward, what's the probability of pulling Ted's name out of the hat?
1 out of 10.
1 out of 10, right? That's the probability of Ted. But then we've got to multiply that. And then what would be the probability of Sue? Ashley, what do you think? Probability of Sue. 1 in, not 10 because we've already pulled the name out. So because we pulled the name out, it's got to be 1 in 9. So it changes it, that first event. You pull the name out, so there's only 9 left in there, and therefore it's going to be 1 in 9. So you can see there's a pretty high probability of this happening. So we are 1 in 90. So that's not easy to get 2 names out of the 10 to be the 2 names you want. 1 out of 90 times before that happens. And look, you may go 200 before you get it. It's just probable that about 1 out of every 90, you'll get those 2 names out. But the first affected the second because we pulled 1 name out and there's 1 less. And that's the situation, and that's how that goes. So we can do the same thing here with marbles. You got a bag and it contains 30 marbles. 12 are blue and 18 are clear. So go ahead and figure out, just do number 1 here and wait for me, and then we'll do 2. Figure out the probability of a blue and a clear. So you're going to 30, mine's bigger than 30. No. I just want the bottom of the fraction. Nathan, what's your bottom of your fraction?
I have 260.
Okay, I have something smaller. Daniel, what's the bottom of your fraction? Colby, what's the bottom of your fraction?
295.
295. You sure it's a 2? Hannah, what do you got? 145. So it should be 36 over 145, just reducing. Right, it should be 12 over 30 times 18 over 29. There are 12 blue out of 30 possible marbles in the hat, and then 18 clear out of 29 now marbles in the hat. And so the probability is 36 out of 145 attempts to get a blue and a clear. So you're talking here roughly, if I go 35, that's 70. So a little less than 1 out of 4. Little less than 1 out of 4. By the way, take your calculators. Let's do this as a decimal, or let's do it as a percent. What is that in percent form? Tell me 36 over 145 in percent form, and we'll go to 1 decimal place. Percent form, 1 decimal place. Brendan, what do you got?
24.8%.
24, how many agree? 24.8%. Okay. So again, as I said, a little less than 1 in 4 probability of pulling out a blue and a clear in 2 attempts, keeping the marbles out once you pull them out. Any questions on how I got 36 over 145? Anybody? Quite a few of you guys were wrong on your denominator. And again, we're just looking to reduce before we multiply, right? Otherwise, you got a mess trying to reduce it later. And why would you multiply then unmultiply to reduce? Doesn't make any sense, right? Questions on that? Anybody? Questions? Bibos? All right, do the last one. What's the probability of a blue and a blue? Blue and a blue. Blue, blue. Aaron, what do you got?
24 out of 145.
And this one is 24 out of 145. So a little less. Oh, I have it right up there, don't I? So a little less in this situation. Because you're 12 out of 30, then 12 out of 29. Just the way it is. By the way, could the probability end after the first marble's pulled out? Yeah, right? That attempt could go, because what if you pull clear out the first time? You can't get blue, blue. But again, that's just 1 attempt. And if you tried it about 24 out of 145 times, you'd pull out a blue, blue. Seemed like it'd be easier than that, doesn't it? But again, that is, and that's about 1 out of 6, about 1/6, about 18, 19, maybe 20% is the probability. All right, grab your books. I just need to read a few. Want to make sure that you can recognize independent or dependent. So page 442 in your books, please. 442 in your book. I want everybody thinking. I'm going to ask you for your answer each time. So question number 1. So again, you're going to say either independent or dependent. Flipping a coin twice in a row, is that independent or dependent? Flipping a coin twice in a row. Here we go. 1, 2, 3. That is independent, because no matter what you do on the first flip, you won't change what's going to happen with the second flip. It has no effect on it. So the flip of the first coin has no effect on the flip of the second, so it's independent. All right, number 2, spinning a spinner twice in a row. So again, what you're thinking, does my spin the first time have any effect on my spin the second time? All right, so on 3, 1, 2, 3, that's also independent. Using a spinner number to determine the number of times to flip a coin. So you're going to spin a spinner, and whatever the number is, that's going to determine how many times you flip the coin. Independent or dependent?
Dependent.
That one's dependent, because the number of flips is determined by the spinner number. What you do the first time determines the second time. Choosing 2 letters for an ID code if the same letter cannot be chosen twice. So you're going to use an ID code with 2 letters, but you can't use the same letter twice. Independent or dependent, class? That is dependent, because the first one knocks out a number or a letter. Number 5, choosing 2 letters for an ID code if the same letter can be chosen twice. That one would be independent. Choosing a class president and then choosing a class vice president. That's dependent, because you knock a person out because they're not going to be the president and the vice president, right? That knocks one person out, and therefore it's dependent. Number 7, choosing a 7th grade class president and then choosing an 8th grade class president. That's independent. Number 8, selecting 3 members of the class to form a committee. Selecting 3 members of the class, that one's kind of obtuse, but that would be dependent, because once you get a person on the committee, there's only so many left for the second person, only so many left for the third person. Selecting 2 marbles from a hat without replacing the first marble. Which one is that, class? That's the dependent. Whenever you don't put it back, then you're reducing the number of choices. And the last one, selecting a marble from a hat twice with replacement between draws. You're going to put the marble back in. That one would be independent. All right, that's the idea. Independent and dependent events. Remember, independent, the first does not affect the second. Dependent, first does affect the second. Take that into consideration. You've got your homework there. Last assignment we'll review tomorrow. Test on Wednesday.